Okay, we are live. Good evening. Welcome to this month's September 2023's version of the Varahamira Science Forum's monthly lecture series. We have a presence on the website. We are on YouTube, we are on Facebook, we are on WhatsApp, we are on several social media. So we welcome all of you viewers to this program, this month's program. We can go check out our website. This is the address varahamirasf.blogspot.com. And you can see videos of most of our lectures recorded and uploaded both on our website and on our YouTube channel. We are on multiple social media, as we said, Facebook, Twitter, Instagram, YouTube. You can go to all of these. Just search for Varahamira Science Forum. You'll find us. So information will be there. We are running a couple of WhatsApp groups also. These are discussion fora where we can just join us. We talk about the lecture of the month, but we also talk about all things science that anybody is interested in. We share video links, articles. We sometimes have debates and all that. These are the contact numbers of some of the admins of the WhatsApp groups. So you can just message us and say you want to join the YSF WhatsApp group and we'll add you. We are started this forum a few years back. I'll give a brief introduction to Varahamira Science Forum. We started this forum in 2017 because most of you know that Madras had been declared the cultural capital of India around that time for multiple reasons, including the December music season, several programs, and so on. And as part of our culture, I thought some of us thought science is also part of our culture. Should we not consider that? We should have some programs regarding science. And nobody was, there are not many public forum popular lectures, and they are not being recognized before that time, or at least we are not coming to know about them. So we started a WhatsApp group to notify each other about science lectures. But we thought that's not happening very often, so let's start our own forum. And we, because the seminars that are happening sometimes are very professional, only for targeted professionals and so on. So that's why we started this forum. At that time, there are several events taking place. I mean, it's not just lectures here and there, programs here and there. The Birla Planetarium, very relevant to our program today. Planetarium is there. They organize a lot of regular viewings. They had organized a Venus transit program, the Mercury transit and all that. Some of us have attended. I never tire of saying this. It's very, very relevant, especially to our latest, today's talk also. Madras is one of the few cities where we can actually go to the rooftop and see a rocket launch, literally see the rocket take off from Sriharikota. Not the first couple of seconds or few seconds, but once you go to the rooftop, literally the photograph on the left is from my house, from my rooftop. The photograph on the right is from Kottrupuram, from the Anna Centennial Library windows. So, Madama, Maile, we can see the rocket launch from the here. VSF, we had several lectures on several topics, some of them by professionals, some of them by amateurs. One of our most popular talks was a talk by Mr. Professor Arvind Gupta. He gave a talk called Science Through Toys. It was extremely popular. We had recently, then a meteorologist, K.V. Balasubramanian, talk about weather and climate references in Sangam poetry. You can see the range right there. We had a Professor Uttara Dorairajan of the Digivaishnav College talk about Leelavati's daughters, women scientists of India, a rarely handled subject. We had Aparajit Ramnath of IIT Ahmedabad University in Gujarat. He gave a talk about the birth of India's aircraft manufacturing industry, which is not very well known. So a wide variety of topics related to astronomy, space, etc. I personally have given a talk about the astronomy and mathematics of ancient civilizations, Sumerian civilization, Egyptian civilization, Greeks, etc. We had Akash Narayanan, who's doing research in the Fermi Lab in Illinois. He gave us a talk on the story of light. We had some students from a local school install a sundial in their school. That is Professor Swaminathan, IIT retired professor, was mentoring the teachers. They set up a sundial, try to understand how a sundial works, and then the teachers then taught the students. We actually run a couple of workshops related to astronomy. Specifically, this is kind of older material, not the latest, Indian astronomy and mathematics. We did it for English and Tamil. We did it even for kids and adults and so on. It's a 5-6 day workshop, a couple of lectures online or in person. We even did one in a couple of unusual mathematical aspects. One of our organizers for volunteers, Badri Seshadri, gave a couple of workshops. One on Kuttaka of Aryabhatta and other on Bhavana and Chakravala of Brahmagupta and Bhaskara. These are about very unusual mathematical procedures that are very useful but are not part of the school or college syllabus today. Couple of years back, we had a talk by Deepthi, who was a fresh graduate, just did her master's. She talked about one aspect of astronomy and how we are all about stardust and Indian astronomers and later discoveries and so on. Then we had last year we had a talk by Mr. Murali Meenakshi Sundaram on the James Webb Telescope and what that is accomplishing, what information it is providing us, or what new views of the universe it's giving, and so on. And that was very topical at that time. And today we are very excited to invite Mr. Suresh of the SAC in Ahmedabad, which is one of the several groups of the Indian Space Research Organization. He's going to talk about Chandrayaan, specifically the incredible journey of ISRO from Chandrayaan 1 to Chandrayaan 3 and the landing. So without further ado, I will pass it on to our friend Ramanan to give an introduction to the speaker, and then we'll hand over the mic to the speaker of the day. Ramanan?
That's good. Thanks. Good day, everyone. ISRO as such doesn't need much of an introduction nowadays, but I just want to add some points on ISRO and then talk about the speaker. We know that ISRO is headquartered in Bangalore, but its activities are spread across various centers and units. Okay? For example, launch vehicles are built at Vikram Sarabhai Space Center, which is called VSSC in Thiruvananthapuram. Satellites are designed and developed at UR Rao Satellite Center, Bangalore. Integration and launching of satellite and launch vehicles are carried out from Satish Dhawan Space Center, Sriharikota. Development of liquid stages, including cryogenic stages, carried out at the Liquid Propulsion System Center, LPSC, Valimala, Bengaluru, and sensors for communication and remote sensing satellites also happened there. And remote sensing satellite data reception, processing, and dissemination is entrusted to National Remote Sensing Center, Hyderabad. It is called NRSC. And application aspects of the space technology are taken up at Space Application Center, Ahmedabad, which is where our speaker of the day, Mr. Suresh, is from. Mr. Suresh has an MTech in software systems from BITS, Pilani, and has been working in ISRO nearly for 20 years. He was primarily involved in remote sensing data processing from Cartosat, Chandrayaan, and Mars missions in the beginning of his career. From 2012 onwards, he developed an interest in planetary landing mission technology development and started working in Chandrayaan 2 and Chandrayaan 3. He was project manager for hazard reduction and avoidance system of Chandrayaan 2 and 3. So with this background, I am as excited as all of you to hear what Mr. Suresh has to talk about the journey from Chandrayaan 1 to Chandrayaan 3. So Mr. Suresh, over to you.
Thank
You
you.
can share the.
Thank you very much for the nice introduction. And I'm very happy to be part of today's talk and even talk about the Chandrayaan journey. And the Varak era of when I came to know about it, it was a really very interesting forum where there are a variety of things are really talked about. So I'm very happy. I'm also very much happy to part of this one and deliver talk. And also I thank Karthikeyan sir for inviting me and introducing to BR. Is the screen is visible? Shall I go ahead?
Yes, we can see it.
So already I said the topic of the today's discussion, the incredible journey from Chandrayaan 1 to 3. It's because the Chandrayaan one, we all know that the moon missions are not started very recently. It has been there almost in 1960 onwards. So in ISRO, the journey started from Chandrayaan 1 in 2008, then Chandrayaan 2, and recently Chandrayaan 3. So how it has been shaped from Chandrayaan 1 to Chandrayaan 3, the soft landing on the lunar surface. So that I'm going to brief and take you to in a very simpler manner, not going into too much of the qualities. We all know that there are many questions always come. So why still people are going to the moon? If you see in the beginning of the 1960s, almost for 2 decades, even the moon landing missions have happened during that period. And still the interest to the moon, it has not been declined. So if you see the major reason why is the science or a discovery point of view, you see, the moon is the really the closest cosmic body for which to discover and do certain kind of experiments, and that can be documented very well. And the origin of the moon itself, still it's not clearly understood, though we had a series of missions to understand either from the telescope. If you see the moon observation, this started almost in the 18th century. The Galileo started from the ground itself. Then we sent the spacecraft to the moon. We have landed. We have taken the samples back. There are so many theories have been formed, but still it's not properly concluded how it is really originated, how it comes to Earth's orbit. But there are majorly four theories which is always revolves around it. The another point of view why we attempt to always go to moon, the technological point of view, if you say it is a promising test bed. Suppose the exploration, the mankind always the exploration is being a thrust factor. If you want to explore the outer space, the moon is the intermediate point in which where you can stop, you can generate something from there, and from there where we can continue our deep search journey. So in the technological point of view also, that is going to be the promising test bed to demonstrate many of our technologies for the deep space mission. So majorly, these two are the major reasons why the many of the space missions go to the moon. The theories of the moon origin, such if you see, there are four theories: the simultaneous formation, where Earth and moon were formed from the solar nebula, where our entire solar system formed. Because this would explain very clearly why the Earth and moon rocks are isotopically so similar. But it could not really explain that the depleted the iron on the moon, how that has really happened. Then the another theory comes to capture theory, but the moon formed somewhere else in the solar system and slowly uh, drifted towards the Earth and is captured by the Earth's gravitational force. So this explains the high angular moment of the Earth and Moon system. But at the same time, why the Earth and the Moon wise, if you see the rocks are isotopically very similar, how if it is formed somewhere else, so that it is not able to explain it fully. Then the third theory is fission. The moon broke off from the hot molten earth while the earth was spinning very rapidly. Why the earth and moon rocks are similar chemically and isotopically and low in content. So that theory is satisfied. Again, high angular moment of the earth moon system is it's not satisfied by this theory. They mostly they accepted there is a giant impact which happened to Earth, and because of that, yeah, the impact whatever has happened, that ejecta material from the Earth, which is actually begun orbiting the Earth, and material lost of the Earth, which is actually coalesced into the moon. So this could explain many of the theories and satisfy the people. The moon missing moon iron as most of the material blasted into the space. Moon rocks, Earth rocks are similar, and why the moon's orbit as well as the Earth orbits are tilted. But again, there is a dilemma here. If there is a impact happen, then it also will lead to the capture theory as well. So still, it is not something is very properly understood. So, just I want to give a very brief history about the lunar missions, whatever has happened till date, not too much of the detail, just to give the complete state. It started almost in the 1959 to 1980. During this time period, majorly the Soviet Union and the United States, they were into the Cold Space war, where they were started trying to prove their technical capability. And in that process, you see, there are many missions, flyby, orbiter, lander, rover, and the sample return. All of them happened within the time period of 1959 to 1980. The Luna 2, which is actually first man-made object by Soviet Union to reach to our lunar surface. Though it did not had any propellant or something, it's more like impactor. So it went and impacted onto the lunar surface. Then Soviet had the Luna 9. That is the first spacecraft to achieve lunar soft landing. What we are doing it today in 1966, it is nearly 96 kg kind of lander, but it had this airbag system because it is not landed into the single place. It is going to be land and bounce and rotate, and finally it will go and set. So that is the thing which they achieved in 1966 by the Luna 9. And the Luna 16, first robotic probe to land on the moon and bring back forth to the Earth. And the first lunar rover is Lunar Code 1, and the later part, the 2, they both had the lunar rover. They traveled as long as 37 kilometers during that time. Parallelly, United States Ranger surveyor mission, and they started many orbiter mission, and they landed on the moon as well. So in the phase two, 1990 to 2003, after 1980, this cold space war got over. Then there is a period in which not many missions have happened to the moon. Then 1990 to 2003, maximum to the orbiter mission, because by that time the technology have evolved. You have a better instrument, better science experiment can be done. So you are because of the technology growth, then you can understand the moon to the next scale. So the NASA is sending many of the orbiter mission. Then Japan joined. Then European Space Agency also joined in 3. Then the 2007 onwards, there is a lot of renewal of interest by India, USA, Europe, Japan, China. Then China launched in 2007. Then Russia started their Luna program once again. So this is the brief history in 2 phases, where if you see the earlier we were landing with some small probes, impactor, orbiter, collecting samples. The later part of time we were sending a better instrument. So the 2007 period onwards, the many of the orbiter missions started during that time. So coming to Chandrayaan 1, that is, we all know that is the first mission to moon. So already there are many space agencies, those who had a better knowledge about the moon, and they have many of the instruments which they have. So the orbiter, though many of the aware that Chandrayaan 1 is only the orbiter mission, but it's also impactor. There is one more moon impact probe, which is also carried by Chandrayaan 1, which impacted on the lunar south pole. So this orbiter carried 11 payload, which is science instrument, 5 are from India, 3 from the Europe, 2 from USA, 1 from Korea University. So in total, if you see this many number of this 11 payloads, which we carried by using the announcement of opportunity from the other space agency in the Chandrayaan 1 spacecraft, and we also happy to that the discovery of water on the lunar south pole. So that has been detected by the one of the Chandrayaan 1 instrument, that is Moon Mineralogical Mapper by JPL. So that is the discovery which happened in the Chandrayaan 1 spacecraft during that time in 2008, the launch vehicle what you have that is going to dictate what is the mass you can carry to the moon's orbit. So that time the reliable vehicle available was the PSLV, Polar Satellite Launch Vehicle. So what it can lift off from the ground and place something into an orbit is nearly 1.4 ton. So beyond that, it cannot anyway carry. So everything is sized within that particular mass budget, the payload, the orbiter, the impactor, taking to the moon, orbiting everything. And going to the moon, till now, the ISRO was engaged mostly in Earth observation missions. When you plan to go to the deep space mission, there are many new facilities which we require to build and many capabilities we have to build. The one is the antenna, what you are seeing here, the deep space network, we call DSM, the 18-meter and the 32-meter antenna. Because for communicating with moon, at least you require 18-meter. To Mars and all 32-meter is the requirement. So that has been built before launch of the Chandrayaan. Then we also where they are tracking those satellites when they are orbiting in the moon. Those the control centers have developed. Then the entire science data what we have collecting from this instrument to archive and process, there is a separate center is also is created. So the entire new facilities as part of the Chandrayaan one, they have been developed. The motion profile wise, if you see, as I said, the launch vehicle, that 1.4 ton weight, it can keep it in a place 250 by 320 kilometer. That is the elliptical orbit, whatever this IO you are seeing, initial orbit, it can place it in here only. Because that is will be the limitation of the launch vehicle, that much mass where it can place. Then later on, by doing certain firing the engines there in the orbiter, then we will slowly rise the orbit of the spacecraft by the different burns. That is from 1, 2, 3, 4. Then finally, when the moon is as moon is orbiting the Earth, when it is coming to the point, then you will be burning the spacecraft such a way that it gets captured by the moon. So once it's captured in the moon, then again series of maneuver to bring that into a 100 by 100 kilometer orbit. So this is also one of the capability where ISRO has developed the very precise trajectory design to reach to a moon's orbit, because we have a very narrow error budget what is available. If something is missed, you will completely miss reaching to the moon. The kind of payloads carried by Chandrayaan 1, even today there are instruments which are all the best for the lunar surface, even till date, like the terrain mapping camera. Like the right side you see, this is actually the crater feature. The moon, mostly when we say from the naked eye, it is a very bright and beautiful planet which is out there. As you go very close to it, you will see a lot of craters, many of the impacts which is happened. This is the one of the view taken by the terrain mapping camera. This is the crater which you see from exactly from the vertical, if you see how it looks. And if you look at it in angle, it is mostly like our eyes. So our eye is able to perceive the three-dimensional in front of it. The same way this camera works with the same principle, but it has the three eyes anyway. So this is a 5 centimeter resolution. What it has is the best for the lunar surface today. And we had a hyperspectral imager and the lunar laser ranging instrument and from the X-ray spectrometer and the moon impact probe. If you see in our electromagnetic spectrum, the payloads, what is the vast coverage which it had actually. So this really played a very important role in bringing many of the planetary scientists whose work in the lunar data set. We have created a community of people within India, whether the academia or the industries. There is many people started working on it. So that one community where the Chandrayaan one could create, even today it's able to inspire and give a lot of data to them anyway. And from ESA, they had the other payloads like X-ray spectrometer and infrared spectrometer and atom reflecting analyzer. And from the US, we had two major payloads, that is a moon mineralogical mapper, MQ, which actually detected the water molecules on the lunar south pole, which is there almost from the 0.7 to 3 micrometer range. So this one is the moon impact probe. The Chandrayaan-1 had reached to a lunar orbit. Earlier, because this is the first time when we are going to a moon, there was a suggestion to touch the moon. Well, so because of that, there is a small cuboid, which is nearly 0.4 meter kind of thing, which has been developed. It has a spin mechanism. It doesn't have any propellant. It will be released from the orbit. Then with the spin, it will be keep on controlling its orbit, and finally it will go and get impacted. So it carried majorly three payloads. One is the radar altimeter and video imaging. Continuously, it will image how it really descends, and the mass spectrometer. So it impacted very near to the our lunar south pole, almost 90 degrees south. There is a very famous crater called the Shackleton crater, where it gone and impacted there. This is the one of the very interesting experiment which carried out in Chandrayaan-1 itself, mainly to give some input to the next landing mission. So these are all some of the visualization which I wanted to share. The Chandrayaan-1 earlier already I said it can see really the three-dimensional view of the lunar surface, how we can create. So the DEM, we call it the digital elevation model, which actually gives your three-dimensional representation of your surface, like height values at every point, what is the height and the elevation. Next one is more like a map. So this from Chandrayaan-1 at 5 meter, the spatial resolution. 5 meter means almost at every 5 meter you are able to see certain objects. You will be able to interpret. So that is the kind of thing which Chandrayaan-1 has provided. And we have generated with a lot of amount of data is provided to the many of these geologists. As the moon, as you go very close, mostly it is a cratered body. The entire surface is full of craters only, nothing else. At any place, if you see, you can find a bigger crater or smaller craters, but without them, nothing is there. So everywhere you will see those undulations. There are craters as deep as nearly 10-25 kilometers. There are craters 1 to 2 kilometers deep, and there are craters where the sunlight never reaches. That is the one area where the MQ could detect water molecules the most. So this is one of the visualization, if you see in 3D, how the lunar surface in close-up view, how it looks. Just to show the craters, the impact crater on the lunar surface, you see, suppose there is a sun here, you see the crater is nearly some 8 kilometer wide, this particular crater is. When the sun is here, this is actually casting a shadow on the crater, and this part is getting lit. As you say in the 3D, how is the crater is this impact whenever any meteoroid or anything impact, it throws out all the materials, these ejecta materials, it goes out and spreads. That's why so many boulders and those things we used to see. So this recreation and extracting 3D information is all possible because of the Chandrayaan-1, the payload which has been flown during that time. And the Chandrayaan-1, the planned mission life was 1 year, and after 8 months, it would not survive further. Then prematurely, that particular mission got ended. It lost its communication with the Earth. There is attitude and issues. So the moon coverage wise, you see, the black regions, whatever you are seeing, these are all the uncovered region. Only the gray areas only is covered. So we have not fully covered the entire lunar surface. There are still gap areas which needs to be covered. Since the mission is entered before itself, we could not continue further. So the data, whatever is being collected, that is the first time where we could develop a technology for the many of these things, even processing those data, understanding the moon surface very close and the very better detail. So that is the kind of input is given by Chandrayaan 1. Then almost after a decade of Chandrayaan 1, the Chandrayaan 2 mission is conceived. And since already the orbiter is the default option, anyway, we need to have orbiter because we could not completely cover the entire lunar surface. We need to finish that job first. So the orbiter is included as part of the Chandrayaan 2. Then we had a now taking a lander along with the rover to the moon's orbit. And during that particular time frame, the launch vehicle, the rocket, our say, so that actually decides what you can carry. So beyond its capability, you cannot carry. So it is the top-down approach. What rocket you have, how much it can carry, accordingly only you can plan in. So the Chandrayaan 2 mission, they had the orbiter. They had a lot of they were maybe 13 Indian payload. This time we did not have the other collaboration with the other institutes. It's mostly all instruments are from Indian instruments. That is 13 instruments. One passive experiment on the lander, and the Vikram and the Pragya, the rover for the experiment. So this got the entire thing. So the mission planning wise, if you see how it all really goes, first the question comes: what is the lift off mass of the rocket? How much the rocket can carry? Then comes at what altitude that spacecraft can be placed. Then how much fuel is required to reach the moon? Then minus this, whatever is left out, within this you have to design a system which can safely take to the lunar surface, either the sensor or payload or how it is going to be structured. So everything comes at this particular stage. So this is how the entire thing happens. So whatever the rocket you have, that dictates, and how much you can carry, that dictates anyway. So this is how at each and every part how we proceed. Right. Chandrayaan 2, anyways, the orbiter, lander, rover, all the three were there. And the total mass of this entire thing is 3.8 ton to carry. As you can see in the left side, there's a GSLV Mark 3 is the launch vehicle. That is the only launch vehicle which can carry. That is the heaviest rocket with in that time. So the design wise, if you can see within this launch vehicle, whatever you are able to accommodate is with the lander and rover, the size and height. So everything has to be designed with respect to this. So for landing to a moon, you cannot have a very large leg so that I can avoid all kind of other benefits. So what I can carry, everything is constrained within this particular space here. So the launch sequence wise, though in Chandrayaan 1, we had many of the things that have been experienced launching from Earth and reaching to the moon. So that is a 1.4 ton. Now that has been 3.8 ton. The kind of weight increased from Chandrayaan 1 to Chandrayaan 2. It is really very huge. The orbiter itself, you see, it is nearly 2.4 ton, including the propellant, because this orbiter has to carry the lander also along with it, and it has to keep the put the lander into the moon's orbit first. Then only it can start functioning. After that, lander will take its own path. So the orbiter has to carry the fuel required for carrying the lander as well. So that's why the weight, if you see, it is a 2.4 ton, 1,000 watts of power required, and it carried 8 payload. And designated mission life was 1 year, and now we are at the 4th year. still Chandrayaan 2 orbit is functioning well, and it is giving a lot of data even today. In Chandrayaan 2, like I said earlier, Chandrayaan 1 prematurely that mission got ended. We could not cover the entire lunar surface. So they repeated the same camera here, that terrain mapping camera. It is named 2. Then after that, there are unique science instruments which got introduced in the Chandrayaan 2, which has been never flown for the moon surface. One is that spectrometer, which is a very wide spectrum, 0.8 to 5 range. So within that range, there is no instrument. Is earlier MQ was up to 3, but it has expanded up to 5. And another is the dual frequency synthetic aperture radar is there in S and the L band both. That is also the unique instrument. The another camera is orbiter high resolution camera. This camera will keep 28 centimeter kind of spatial resolution. Anything is there as small as 28 centimeter, you will able to figure out what is there in the lunar surface. Because this is one of the important camera which was required for Chandrayaan to even lander to land, and which also helped in Chandrayaan 3 lander as well. And this is one of the highest camera even today orbiting on the moon. So the Vikram lander, that is 1.4 ton weight, 640 watt of power was required, which had 3 payloads and 1 passive experiment. This is actually the laser retro-reflecting array by JPL, mainly to find out the Earth and moon distance continuously by the passive experiment. The size-wise, it is nearly 2.5 meter by 2.5 meter and 1.2 meter tall. And it was designed for one lunar day. One lunar day is 14 Earth days. And the Pragyan rover, it is 27 kg, very small one, 50 watt of required. It carried 2 payloads for the InSight such experiments. And the dimension is nearly about 0.9 meter in length. So that is the kind of size what it has, and whatever thing that is the solar panel. And the rover, what is the movement wise, the 1 centimeter per second, what speed in which it can travel. You cannot travel very fast. The payload, what it's covered, the lander, if you see the instrument for lunar seismic activity in and around in the, though there are fiction that the moon, it does not have any active thing which is happening right now, but it's also the equal theory that there is some activity which, that the seismic activity which is happening, to record that there is a one instrument flown. Another instrument for the thermal conductivity and the temperature gradient, the chase the experiment is called. So the which actually will able to drill to a 10 centimeter to the lunar regolith to find out the temperature variation. And Lagmir probe actually they conduct the atmospheric studies the lunar surface. And then the rover, we had only 2 instruments, both the spectroscopy. One is alpha particle X-ray spectrometer, another is the laser-based spectrometer. The alpha particle X-ray spectrometer requires hours of time in observing data from the single place to find out. Whereas the laser introduced one, it requires a very less amount of time. With the laser, it will fire, and what of time will get reflected, it will be able to record and do. And the passive experiment is laser retro reflector array, which is there on the Vikram lander. So the challenges in soft landing, what is so challenging in 1969 people have landed, and what is today is so challenging. The major challenge comes today is the difference between the soft landing that time and now. Earlier, the landing error really is what we call where you are going to land. So that is something approximately there, and there is a kilometer of error. They will be landing from 30 kilometer, 40 kilometer, even 60 kilometer away from where they have landed. So it is again, it is called soft landing. But when the land, it's not landing into the single place, mostly with the airbag is bound with an wind. Then later on, with the controlled descent using propulsion, then they landed. The kind of lander which they carried during that time and the error in which they have landed, they are all quite large. And today we are aiming at landing very near to the South Pole where nobody have gone before. And you are trying to go in a very small pocket of a place where you are supposed to land. So that's where the great level of accuracy comes into picture, where your craft is affected such a way that you are able to go to that place very near where you are finding. So that is a major challenge. Also the trajectory accuracy, that is very important. Another is the deep space communication. When you go land very near to the South Pole, that lander to Earth communication and translunar injection. So unlike others, we do a series of maneuver to reach moon. So whatever the calculation you do within Earth and reach to the moon, that is plays a major role. If anything goes wrong here, that was to be a very big issue. Then orbiting around the moon, that is nearly 2.4 plus 1.4 ton weight together, and soft landing on the moon, still a very challenging task going to be near to the lunar south pole. And the lunar dust, there are many data is available on the lunar south pole land when the engines are firing, how much the lunar dust is going to come back and it's going to affect some of your instrument, which later on we have a mechanism of deploying mechanism. If the lunar comes and stick to one place, which restricts for the deployment, then you will not able to any mobility here. So that is one of the bigger challenge. Another is when we are going to the south pole, that is the extreme temperature uh, variation where it goes as close as 120 degrees Celsius to a minus 150 degrees Celsius. So that is the kind of variation what it has to withstand when it is operating there. Then next comes the landing site selection, where you want to land. In Chandrayaan 2 time, we are dependent on the other space agency data for the required resolution. And in the Chandrayaan 2 orbiter, once it was in the place, then later on we characterized before we were landing. And this yellow box, whatever is seeing, that is the landing site. It is a 500-meter by 500-meter area in which our Chandrayaan 2 lander was targeted to land. So what is the constraints here? You see, the slope has to be less than 10 degree. Otherwise, what will happen when the lander lands, it may topple. So the place where you are heading, that has to be characterized. The boulder size, it should be 0.3 meter the height, because when it is there, when the lander lands, it should have to make it topple, because there is the engines which will be protruding. In the later part of the slide, I will show that. And the sunlight part, at least 11 to 12 days. When you're doing an operation there, everything happens through the solar panels. So you require a continuous illumination, and there should not be any big hill which is casting a shadow over the lander or the rover where you land, which actually affects its power generation and the communication to the earth. And the other part also, nothing should be there to really obstruct your communication from the earth as well. This is the highest resolution the camera which is there currently in the moon's orbit. Like you see, the lunar surface in the previous image to the current image, as you see the place, there are a lot of small boulders which has been captured. Because as you go in better detail in the lunar surface, you will find many such boulders. That is very much important when you want to land into a very specific place, whether your lander can withstand the boulder or crater, whatever is it. So that mapping was possible only by OHRP. So in Chandrayaan 2, before it landed, we imaged, then we updated before it was to land. And there is another close-up view. You can see this is the shadow, the region of the crater. This is the rim of the crater. So when the impact anything happens, when it throws out, there is a lot of material comes away. There is thing called the lava, the geology called there is many boulders, many kind of material which is thrown out of the impact, which is lying over there. So the Chandrayaan 2 typical descent trajectory, when Chandrayaan 2 orbiter taken the lander to the moon's orbit, then it gets separated. Then there it will be staying in a 30 by 100 kilometer orbit. So from the 30 kilometer, it will be start descending to the landing place. So in the Chandrayaan 2 30 kilometers started, there is place called rough braking. It has to control its horizontal velocity as well as the vertical velocity so that it is able to move to a place where we are supposed to land. Then there is a place, attitude hold, where the lander will be controlled, not much movement will be happening, where the many of the sensor will be taking measurements to know that where I am, at what altitude the lander is there, and what speed I am traveling. Once those informations are given, there is a fine braking happen. The module will be slowly coming to a vertical for the landing. Then it will be coming as low as 100 meter in Chandrayaan 2, which will be hovering for nearly 25 seconds to find out the below the area is safe for me to land. Is there any crater, boulder, or where I will land, where I have to manage? That information, once it's available, it will land here. So in the Chandrayaan 2, up to this particular point of view, everything happened very well. Then after that, we all know there is a problem happened in from the fine breaking onwards. So it could not reach to the designated place. It is deviated from here itself. So the failure analysis report and our chairman, current chairman himself will given a 1 hour lecture on exactly what has happened. We will go through, we'll get more detail. And the Chandrayaan 2 lander, it could not make a successful soft landing. The Chandrayaan 2 orbiter, even today, it sends a lot of data and it's covered almost the entire lunar surface in a different spectrum, like a terrain mapping, the camera, which gives you here, you see the 3D view of the crater and the spectrometer. There are 256 bands of the lunar surface giving the data, which is available to a general public to analyze and for everybody to access. Every 2 months time period, the data is released in public domain for people to access and use. And even today, it is active and it is keep on giving a valuable data. So that is a very big outcome from the Chandrayaan 2. And the camera, what we had in Chandrayaan 2, that only we have used for even Chandrayaan 3, even to fine tune as well. So moving to Chandrayaan 3 mission, which is like Chandrayaan 1 to Chandrayaan 2, it's a decade of time. Chandrayaan 2 to Chandrayaan 3 is within 4-year time period. Now, when Chandrayaan 2 started, we did not have had any orbiter in moon's orbit. So we have no means of getting any image from the lunar orbit. But when the Chandrayaan 3 mission concluded, that time we are having the active Chandrayaan 2 orbiter, which is having a wealth of data, what is required for you to consume. So the Chandrayaan mission considers only landing mission, nothing else. So the entire concentration is given only to lander and the rover. But again, the launch vehicle, what you have is again same. So the weight what you can carry, again, it remains same. The only advantage what I've got here is instead of orbiter, there is something called a propulsion module. Because from Earth orbit to the lunar orbit, it has to be carried. by some means, either it's orbiter or any other means, it has to carry. So it requires a lot of propulsion, by which there is series of maneuver which happen when it takes this lander to the moon's orbit. So in the Chandrayaan thing, that is called the propulsion module, the weight of 2.1 ton, which is there active in the orbit for some time. So it carried one payload, though it is there in the lunar orbit. It is a spectropolarimetry of habitable planet Earth. So it's called the shape payload. Like it will be continuously observing our Earth, which will give an input when we want to explore some exoplanet signature on the outer space. At what kind of signature we will be really looking for? How if we correlate with our Earth, that we can say that okay, there is other planet which also is more like Earth. So for that purpose, it is a very small payload which is put on the propulsion module. So other than that, nothing major. So its major job is to take the lander to the moon's orbit. Then the advantage what we have got is this 2.1 ton. The earlier orbit was 2.4 ton. So that 300 kg mass transfer to the lander. We increase the propellant storage and we increase the redundancy. And if you see here, really it was 1.3 ton, now it's 1.7 ton, and 738 out of the power it can generate. And the kind of specification, whatever has been built for the Chandrayaan is really very huge. In all the level, it has been increased. And rover wise, it is exactly kept same. So the no modification done to rover, and in the lander, for all the landing sensor, all the improvement have been done. The science instrument wise, the lander also had the same thing. Then coming to Chandrayaan 3 landing site, where we are supposed to land, there are 8 landing sites over the South Polar region have been studied. The same criteria, your slope, boulder, crater, all those things, how the distribution is. The major change is in Chandrayaan 2, we had only 500-meter by 500-meter landing area. In Chandrayaan 3, does increase to 4 kilometer by 2.4 kilometer. It is mainly the error bounds are increased. So anything happens to the lander, any deviation is happening, at least I should be able to land it safely within my designated place. So for that, the landing area is increased. The green one, whatever you are saying, they are all the safe to land. And the red ones are the hazard. And dark blue, whichever you are seeing, that is the number of spots. In this area, nearly 3,900 spots are there where the lander get the opportunity to land. Like typically, if you see when the aircraft lands at the 200-meter to 300-meter kind of the runway is created where it is flat in nature, not variation is there. There is no obstacles in and around. So like that, when you look in lunar surface, it will not is not possible anyway. So the place where you are going to the South Pole, you have to find a place where slope is very less than 10 degree and not much boulders are there. They all should be less than 32 centimeters, and we should have a continuous sunlight over that region, and we should have visibility to the earth for the radio communication. There is no local terrain features like a hill or something which is casting shadow. So which are the major criteria has been studied, and this landing site is increased to a such bigger area to make the Chandrayaan landing very safe and successful. A host of sensors, if you see, these sensors we had in Chandrayaan 2 as well, the laser Doppler velocity meter, which is a new one which got introduced. These sensors, which are all the majorly required for the safe landing, like altimeter. There is a two altimeter, one is laser based, another is RF, the radar based. Velocity meter, one is the laser Doppler, another is camera based. Then inertial measurement unit. and accelerometer. Both are there. And propulsion wise, we have a 800 Newton core engine and 8 thruster, throttle thrusters, and the navigation guidance and control, which actually controls from the power descent to till the touchdown. That is the central unit. And the hazard detection and avoidance, as I said it earlier, when the lander finally reaches to a place, it has to decide where I have to land. Below me, is it really safe to land? Otherwise, it has to be uh, specifically instruct what is the place in which it can land with error bounds. So that is one other important sensor. Then landing leg mechanism when it goes. So if you see when the lander is descending, it's 1.6 kilometer per second is the speed in which it is actually descending. Then continuously it has been controlled to the touchdown velocity of less than 2 meters per second. So when it is touchdown, the slant like mechanism has to withstand those things. So with the rover testing, what was the rover carried by Chandrayaan 3? If you see, this is actually lunar simulating the soil, keeping similar kind of the soil what has been created here in the lab environment, and with a different folder whether they are able to climb and be able to navigate properly for the different kind of test which has been conducted in the lab environment as well as in the outdoor. And the descent trajectory wise, it is very similar to Chandrayaan 2. There are changes here in the when it will come after coming to the fine breaking phase. You see in Chandrayaan 2, all were good to this point of time. Then after that, it has to be really vertical and come here. In Chandrayaan 2, we had only one hovering, and here it has been changed to two hovering at 800 meter and 500 meter. So when at 800 meter, when it is hovering, it will take input from altimeter, velocity meter, at what altitude. Really, I am at 800, or I am, what is the error I am having, or where I am moving horizontally, I have moved how much. This information it updates. Then it designs. Then it comes to 150-meter altitude. Then it holds there for nearly 22 seconds to see that where I supposed to land, whether I am in a place in safe or whether I navigate to a place where it is safe to land. That is a hovering too. Once that is told, then it will slowly it will control its vertical and horizontal velocity. Then finally it will come and touch down. So this is a typical descent trajectory of Chandrayaan 3. And this hazard detection and avoidance system were majorly involved. There is a camera called the lander hazard detection and avoidance camera. When the lander is hovering, which is there at 150-meter altitude, like you can see, it will take an image and see that is it really the safe. As you see, there are craters and boulders and many things are spread across. Then finally, it is actually instructing the lander based on the onboard stored one. This entire scenario is nothing is the ground command. It is complete automatic landing sequence. So it has to decide on its own what it has to do next, and the feedback, whatever it is getting, accordingly it has to divert. So when it is hovering, there is an onboard map. It tries to check and see that where I am. When a 4 by 2.4 kilometer, the lander can be anywhere in that place based on the navigation error. So then finally it needs to know where I am right now. Once I know where I am, which is the place I can land, then that comes the other detection and avoidance to tell, okay, this is a place safe for you to land. Once that feedback goes, then lander slowly listen and finally it goes and touch down. So the minimum 24 meter by 24 meter safe area is given to lander, though its entire the diameter of the land, you see the nearly 4 meter. So to have other kind of error also into the account, we have given a minimum 24 meter by 24 meter so that any error means it doesn't get into any issue or it goes land very near to the crater. Like the first landing, soft landing mission done by Luna 9 with airbag mechanism. though it's soft landed and it's keep on jumping and rolling. Finally, it almost reached to a place, to a very tip of the crater. If it would have rolled one more, it would have gone deep into the crater. So that kind of thing it should not do, because after landing, the next thing is rover has to come out. It has to roam. So it also require a place to roam around. Its difficulty level will be still very high because it's very small in size. The wheels are very small. It cannot climb very big boulder. So accordingly, the area has to be selected anyway. So in the Chandrayaan 3, during live, you might have seen at 150 meters, the lander was keep on hovering for 20 seconds. Then finally, it has got some signal from exactly from this HDS system and told that, okay, you descend and land where you are. So from there, it has came down and it's landed into a place. The this is the one small video, the hovering, whatever I was explaining in the previous slide about at 800 meter and at 150 meter. We also had the onboard camera, which was capturing the continuous process from 30 kilometer to till touchdown to have the contextual view and later analysis as well. So this one small video just to show. This is the first hovering point at 800 meter when it has come. So it was coming and hovering. You can see that it is waiting here almost the view within which though there will be a slight movement will be there, but it is there for only 20 seconds. So within this 20 seconds, it is updating its all its sensor, altimeter, velocity, everything. Then finally, it is proceeding vertically down to 150 meter. So when it goes to a 150 meter, this is the place, this is the place at 150 meter when it is coming and hovering. And at 150 meter for nearly about 20 seconds when it is hovering there, when it got its safe location, then finally it will go and back to a place. So the video is taking time to play.
If the video is getting stuck, you may want to go to the next slide and then start sharing.
Yes.
We should also presentation.
I'm sharing it again.
Okay.
Okay, this is it. Yeah, is it visible now?
Yes.
So this is the first hovering when it holds here for 20 seconds, then after that it goes. This is the second hovering at 150 meters. So once it has got the safe location, then in that it is now vertically down. The last one, whatever we are seeing, almost it reached to a surface and the plume which hit the ground, it is essentially becoming. It is the last one. And this is the bottom one, whatever you are seeing, that is actually the lander leg, how it is going and resting onto the lunar surface. So immediately the post landing, as we said earlier, the Chandrayaan 2 orbiter, which is really active right now, which captured our Chandrayaan 2 lander as it's landed. you can see it is almost in the beginning of the day in lunar surface. It is almost the second day as per our Earth day to calculate. There it is nearly 9 degrees of sun elevation. So sun is rising there. So that is why you see here this lander actually is casting a very large shadow here. So that we are able to pinpoint it is because of the orbiter high resolution camera which is there in Chandrayaan 2 orbiter. Then this is the lander image which captured by one of the camera called a nav cam, which is there on the rover. So this is what happened when the rover is came out of the lander, when it is there in front of the lander. It has taken the image of the lander. As you can see, the lander leg, so the structure, whatever is given, if there is a very hard surface, it will get crushed and it may go inside also. If you see, it is exactly resting. So that means the place what we have selected, it does not have any very big boulders and the craters on the surface. The roughness is relatively very good for the lander to even say plant. This particular lake it is there in a very small crater, and there is a slight slope is there. As such, in the horizon, you see the entirely, you are not able to see any bigger boulder. So this is the one of the important thing for any landing mission, the landing site characterization when you do by any other sensor data, how best that has been selected when you are going and taking an attempt. In the bottom of the lander, you see there is this all called the LAM, the engines actually which will be firing when it is descending. So the any boulder, suppose if it happen to be here, it will topple the lander as well. So that is why the boulder size is very much important. This is another one exactly after the post landing, the ramp actually got deployed. The rover actually was there in the inside the lander. So it is in the stored condition when it is deployed. After deployment, the rover has gone off to the place. There is you can see the very small crater. So this crater is of less than a meter kind of a size. In the moon case, the diameter to depth ratio, if you see, is nearly 0.25. Whatever the diameter, 0.25 of the is the depth anyway. So the any crater you see, whether when the rover is going, whether it will able to get inside or will it able to come out. So based on the diameter of the crater, we will able to estimate. But in the rover, we also have the other camera to find out the height. As you can see, when it has gone out and traversed in the lunar surface, the soil is so fine and the back which actually compressed the entire region. This is another interesting image captured by the rover NavCam. This is the one track where the rover has traversed up to this place. So when it has gone to this particular place, there is a crater which is there uh, here, and when it cannot travel further, and this side also there are craters. So it cannot make anything further then. So it is traced back to the same position when it has traveled here. So that is a track what they're able to see. It has gone the place and be able to come back to the place where it is started. And this will be another the experiment on the September 3rd. It got conducted the lander hopping operation. We are left with a lot of fuel in the lander because there are for the many contingency it always carries some considerable amount of extra fuel so that you are able to cater to any of the other contingency requirements. So whatever fuel is there, like Chandrayaan 1 orbiting impacting was the objective. Chandrayaan 2, the orbiter as well as the landing was the objective. Chandrayaan 3 landing and roving the objective. So in the future, if anything, any other experiment if you do, then if you want to bring back samples from the lunar surface, You have to land, again you have to lift up from there and it comes to moon's orbit, then from there again back to Earth's orbit. So to experiment that, there is one operation called as lander hop. Using the fuel, it is fired for 300 milliseconds, where it has gone up to 40 centimeters. Again, it has landed back. So that for the one accident, you can see the lunar plumes are started coming from the plume engine. Then it is finally again it is landed to the place. It's nearly displaced by 30 centimeters from that particular place. This is another interesting image because many people had a doubt that when the lander, once it is deployed its RAM, for hop operation, there is also option to again store back the ramp, whatever is deployed. The rover is anyways out, this ramp are again stored back, it is attached again back to lander. All the deployed mechanisms are again stored back. Then the hop operation is happen. So this is the ramp when the lander is landed, how that time. This is the post hop operation. Doing the comparison of that image, you can see the shadow direction. This is the actually this is the east. So when the sun is rising, you see the shadow is that direction. And this is almost the 3rd of September. The sun is going to set. So the sun has gone to the west side. The direction of the shadow from this direction to this direction has changed. So there is small amount of time I spend in the rover. So rover when it has to navigate, like we have a 2 eyes. The rover when it is there on the lunar surface, it has a 2 navigation camera, like this one, which is stereo camera, exactly like our eyes. It takes the 2 image, sends to ground. Then we find out what is there based on the elevation profile crater, boulder, where it can go. The path is generated. Then again, it is upload back to uh, rover to move. Then after that, the rover moves. Anyway. So this is how simply it is done. And there are certain mechanism by which the rover is actually was placed inside the lander. This will be all will be in stored position after deployment. The solar panel will be deployed. Whereas the holding mechanism will be there that will get released before it rolls down. The right one is the image which is taken by the 2 different view. It has been combined together to create another. You can use a very simple this red cyan glasses to view these images in 3D, which will give a very perspective 3D effect of the crater and how the terrain is really undulating. It will be very interesting to see. So the lander location wise, this is where the Chandrayaan 2 was to land, and what we have landed right now is Chandrayaan 3 September is here. And the Chandrayaan 1 impact point was exactly in the pole. So data set wise, there are a lot of data sets available globally as well as by the Chandrayaan missions. If you see the terrain mapping camera, the 3 data sets is what is available from Chandrayaan 1, even Chandrayaan 2. They're all really the best available data sets globally. At 5 meters is the best available today in the 25 centimeter data as well. And the hyperspectral data wise, if it is moon meteorological mapper, it is a 0.4 to 3 micrometer, where Chandrayaan 2 is covering from a 0.8 to up to 5 kilometer up to goes up to the thermal foundation. And the SAR data, we have the 2 meter of resolution to up to 75 meter. These are also some of the places where you can have access to all of our Chandrayaan data sets, whatever I talked about and whatever till date we have data. This is the place isldcga.in. That is our ISRO Science Data Archive. We process, we host every data. After 2 to 3 months of reception of the data, it will be available here. There are the other websites for conditions sake I mentioned, where we will be able to get access to data sets from the other space agency as well. So the scientific research and training, especially the space application center at Ahmedabad, We take many interns and training and there are the people we take from the wide variety of backgrounds, from the B.Tech to MSc, in all subjects, emotions, in GS, atmospheric science, earth ecosystem, meteorology, oceanography, computer science, electronics, communication, mechanical, because this entire wide spectrum of this one is also covered. They can apply very well for their final year project or even the long durations are preferred. Generally, they can stay for quite long time, even 3 to 4 months for some kind of study project if they are interested also. This is a link in which they can go fill their details and they will get called by their. Thank you very much. Thank you.
Thank you, Mr. Suresh. If you can stop sharing your video, stop sharing your presentation, and then just keep your camera on. Gopu, we continue on YouTube, right?
Yeah, you can have the interaction with him.
Sure. Okay. All right. First of all, thanks for the lecture. We found this very educative, and some of the terms were broken down into very simple concepts and explained in a very simple way. So thank you so much for that. I have a bunch of questions, and we also have some questions that are coming through our live YouTube. So we will switch back and forth between some of my questions and some of the questions that are coming on our live YouTube. First of all, you mentioned that when there is a transition happening from the Earth's orbit to there is a transition that happens from the Earth's orbit to the moon's orbit, right?
Yes.
Throw some light on what exactly happens there.
Yeah, actually, what happens when the Earth to Moon distance is 3.84 lakh kilometer the distance, entire distance. The rockets cannot place the spacecraft to near to the Moon's orbit. So it is leaving to the Earth orbit, nearly 200 kilometer kind of orbit. So it is an elliptical orbit, 200 by 36,000, which it is orbiting. Then what happens when it comes very near to Earth? There is the engines are there which we fire. So when you are firing, it gains a momentum when it goes to another orbit. So like it is like the orbit racing. So from my 200 this 23,000 kilometer orbit, slowly I am raising my orbit, which goes very near to Moon, because Moon is also orbiting. From the trajectory calculation, we know that when we are firing our satellite, when it is going to reach very near to a moon. So we also know that precisely how the moon is moving. So as the moon comes very near, then again we fire our rockets, which is there as part of the engine, as part of the satellite, to get captured by the moon. So that's what the transfer which we do from here to there.
Right. Okay. You also spoke about, the propulsion module or the launch vehicle, which is housing the lander and the rover. You also mentioned that it needs to hold within that, right?
Yeah.
Give us a sense of what happens, when you are engineering or designing the vehicle. Is the space constraint fixed first, and then the other components are, back engineered from there? Or is it what kind of thought process goes in that design? Is the space constraint first a given and then reverse engineered, or is it the other way around? Throw some light on that.
Yeah, so that the space constraint is given first. So like GSLV Mark III rocket, if you see, at the most it can accommodate less than a 4-meter envelope what it has. The payload pairing what it got. You might have seen many of the launch videos which get separated. So beyond this, it cannot house anything. So when you are having that space constraint, anything you design, it has to be accommodated within that. So it is a top-down approach. What space we have, what weight we have. From there, it is slowly worked out. Then accordingly, the design constraint, everything built into the orbiter, lander, everything. So that is how it is worked out.
Right. VK Srinivasan has a question. which is how our lander rover is different from the China's Chang E4U22 rover.
Yes. So the Chang'e lander and the rover, you see, they have landed in there is some, in the moon, there is two kind of place which we call. Even our naked eye, if you see, there is a place, something very dark in nature, another place is very bright in nature. In the moon, even our naked eye also we will able to make out. So that the dark in nature area is called mare region. There will be low reflecting region, and the bright ones are high reflecting region. So where they have landed, the Mare region, relatively not much craters, boulders will be there. It is very flat terrain what you will get in the equatorial or in the northern hemisphere. So Chang'e is chosen that particular place. So they have the flexibility of landing it in a very larger area. They will able to land it in a place. They will not get into any kind of issue. And the lander, whatever they had, unlike we had one camera, the lander hazard detection and avoidance. This is the first time in a lunar surface it has been used for landing one. Otherwise, for any other mission, the Chang'e one, they have used something called the flash lidar, which actually in the real time it will be taking the lidar based observation, then it will be finding out where to land. The problem with that is that it requires a very heavy amount of the mass to be carried, and the power requirement will be higher. And the Chinese, the lander, whatever they had, the hazard avoiding capability is high because their landers are somewhat bigger than ours, because their launcher had a bigger capability. Okay, so that is bigger. And the rover is also bigger one. And they also carried the radio isotope phased heaters, which can survive this lunar cold night. But like we had only 14 days only because we did not have any radio the heaters there to keep our every electronics component under the comfortable temperature in lunar surface. But they carried that one. That is why that particular rover is still surviving. It is able to make a lot of measurements. So the major difference wise, they are the different, and they also had the different kind of science experiment as well. They have anyway carried away.
We have a question, a very similar question from VK Srinivasan and Vidya, which says, is the Pragyan rover now kept inside the lander during this period?
No, it is parked outside only.
Okay.
Because it cannot again go back. Whereas the lander ramp that can be stored back, all the instrument can be stored back, but the rover cannot go back inside. There is also another logical problem because as the sun rises there, so already we are attempting to wake up the lander back. Now it is morning, it's already started in lunar surface anyway. So it has to be in a place where it can receive solar energy, the sunlight, so that it can charge its battery. So it has to be outside only.
And is that why you had listed? Because I was curious when you wrote one of the points on your slides, which said that the landing surface needs to be sunlit for 11 or 12 days. Is that the same reason?
Yes.
Okay.
Because it's purely operated by the solar energy only. So if it is not there, it will not be able to survive. So that is also one reason.
Another fascinating thing here is the list of experiments that you had listed both in your Chandrayaan 1, 2, and 3. How what thinking goes behind what kind of experiments have to be done? For example, you decide that you have to deploy a spectrometer, or you need to monitor your lunar seismic activity or your camera infrared. What inputs or what thinking goes behind that decision? When do you decide what kind of experiments have to be done?
So before these missions are conceived, there is a sequence of science working groups in ISRO, what they call. The group of scientists come together. They discuss that whatever experiments happen till date on the lunar surface by the different instruments, and what knowledge system we have right now, and what are the gap areas that they identify, even interacting with the international scientists as well. Then they find out a place, the gap areas in which the measurements or the experiments which we have to make. Then accordingly, those requirements are derived first from the science working group. Then to fill that gap area, this is the experiment we have to do. Then what kind of instruments are required? Then the instrument design happens anyway. So this is how the in a simpler manner it goes for any mission. Always science working group, the people who discuss and find out where is the gap area and what we need to do for any future mission, like any future Mars mission or the astronomy mission. The discussions generally happens almost as early as 10 years or to 5 years before. So we'll be keep on discussing to find out this configuration. Then finally it comes to the realization.
Right. Okay. So it is a well oiled, well thought out
Yes, yes.
mission. One additional question from Vidya on YouTube is, can you shed some light about the temperature on the lunar surface, which has wide variations within few centimeters?
Yes, so earlier mostly people observed from the remote sensing about the lunar surface. Like we have our own instrument, the IARS, the spectrometer, which had up to the thermal band end. So we have observed over the South Pole, there are places how much the temperature can go as low as to one place, but that will be in a very wider scale, almost up to the 80-meter, 100-meter scale. So this is something like a very in situ experiment what is carried out. From this is the first time which has been observed in 10 centimeter of regolith in the lunar surface. We have a variation of nearly 40-50 degree of temperature down, which is happening in 10 centimeter. So this is the first time which has been analyzed by that particular instrument. But we have collected a lot of data. It is being studied further, okay, which really makes this, and because this gives one possibility in future for the lunar settlement or exploring the other planets. When you go there, you have to stay there for a long time. So whether if you beneath the lunar surface, if you make something, whether that will be very easy for lunar habitat or something. So that data is still continuously it is getting studied further. But currently could say that the temperature variation in such a small of 10 centimeter, there varies from 40 to 50 degree of variation what is happening. That is the reason in lunar South Pole there are many craters which is permanently shadowed. There is no sunlight goes there at all. The water molecules, whatever is found, they are all trapped there only. So that only is further missions and studies, whichever is aiming for, they are all going very near to mainly to quantify how much, okay, water is there, in what form, and how much in content.
Right.
I have a question, Suresh. Why are we using only a wheeled robot? Can't you use a robot with legs instead of this thing? If you make a motor with a rover with legs instead of wheels, can't it travel a greater distance and not worry about falling into craters and so on? Is the mechanics too difficult?
Actually, sir, there if you see the lunar anyway, no, it is 1/6 of the gravity as such is anyway. So when you make something is standing very tall, controlling that particular structure, then accordingly it has to be the center of gravity has to be adjusted such a way that it is able to hold there. Okay, so that makes the structure very big. So that big structure will not be able to accommodate. As such, you see our rover, it is nearly less than a meter. That much only we are able to accommodate within this mass budget. So when you make this structure, they become a very big, like Luna, the instrument, if you see, it had a 6-wheel rover and it has traveled 37 kilometer during that time. Even today, even at Mars, none of the rover have traveled that much anyway. So their main motto was to travel as long as possible with bigger wheels anyway. One is traveling. Another one is what makes some science interest. Like currently, when Chandrayaan 3 rover was roaming, there are craters mostly formed a billion years before. There are craters afterwards, something called young craters and old craters. When you are going to a place where you are able to find out a regolith and boulder, when you are making a science experiment, then people wants to stay there for more time to make some more experiments anyway. It's not only about traveling, how far you are able to travel, and also the scientifically interesting area, how long you are able to stay. So that is also the one factor.
Right, right. There's another interesting question from VK Srinivasan. Is there a sample return mission that is being planned?
As of now, there is no talk about that. But anyway, the future, if at all the next mission, that will be this one. But as I said, there is no official confirmation about it.
Right, right. A project of this magnitude, this precision requires a lot of simulation. I'm not just talking about the computer simulation, but simulation, right? I know that itself is a separate lecture topic, but try to give us some magnitude of the amount of simulation that goes behind. Maybe we'll just talk about your area, right? Remote sensing. What kind of simulation goes on in your area before you get ready for the actual launch?
Yes, so before, especially in Chandrayaan 2, also we did a lot of things. In Chandrayaan 3, that the magnitude of this has been really multifold. One is, as you said, is the computer-based simulation, where in software we do, that is a software in loop. Then all hardware, whatever is meant for lander, that is hardware in loop, that is the one kind of test is done. These are all done in the lab level before we take our sensor, our instrument to the field. So we qualify, and in the field, especially for the landing missions, we test using helicopter, then we test using the different drone, and we test using the crane facility. And also there is different tower cranes are there where the propellants are really fired and the lander is descending and testing. So the kind of testing in the field, whatever is done, that is also quite high. And in the lab, the 6 degree of freedom simulation, the sixth of what we call the Montauk simulation. That is also is done at every system level. One is at every subsystem level it is done. Then also in the integrated level is also it is done. So the amount of time spent on the testing, so that is a quite large than the actual development. What we do.
Right. There is a question from Shanti, and she asks, can you throw some light on the rehearsal for the landing? What goes behind that?
Yes, so the rehearsal, as I mentioned, there are many sensors are there for the landing, which really makes it perfect. So for those sensors, before the landing itself, from 30 kilometers till touchdown, there is a simulation. The trajectory is given, different perturbations are given. Then we see that where the lander is leading to. Is it leading to within our 3 sigma or 6 sigma? At what sigma level it is able to reach, where the dispersion is going. So we have a host of sensors, all has to work. But the space is space. We always have a surprise in space. If there is a critical sensor which fails, it does not give anything. So when you are descending, it will not give any input to you. Then in that case, then the lander has to decide where it has to land. Accordingly, it has to change based on the other sensor input. So in our rehearsal, we do everything. We make all sensor failure. We make certain sensor available. So all kind of combination which we do. Then we see that the lander is well within our bound or not, or where it is deviating. If it is deviating, then what corrective mechanism we can do. So that is the one thing which we do. And also there is something called automatic landing sequence, which is pre-decided from 30 kilometers to till touchdown. So that is also tested here. Exactly similar lander hardware is available in the clean room. So all commands are fired and we see that how sensors are performing, how it is descending, how it is leading to the successful landing. So this is how the it's tested and reversed.
Right, right. Another question, this one again from VK Srinivasan is, how much of this lander or rover concept is reusable for, let's say, a Mars expedition?
Yeah, so the Mars, when you see the any soft landing, the sensors is the most crucial part of the sensor and the navigation and guidance. So this will be again reused, but Mars have anyway the thin atmosphere. Unlike Moon, it has a thin atmosphere anyway. So when it is in the atmosphere, it has the different challenging. But when it is descending and it is has to make a soft landing there, the sensor, whatever has been designed and developed for this Chandrayaan 3 lander, is all will get reused. But of course, it will have its own modification and modeled according to Mars surface. But this will serve as a base for the other landing missions.
Right, and only adjusted for the atmospheric conditions.
The condition and for the Mars landing requirement as well.
Right, right. Is can we also see the Vikram lander using very powerful telescopes from the Earth?
Actually, it is only 2 meters the size. Many people have anyway attempted and they also claim that something, but according to this very difficult from even 100-kilometer orbiter from NASA, but JPL, they could spot only some 5 pixels of our lander. Only Chandrayaan 2 orbiter had a very high resolution. You are able to see lander and shadow. It will be too difficult to spot it because it's in a place that perfect pointing of that particular location with accuracy will be very different.
Right, right, right. So when we say that we are going from certain amount of payload to a much higher level of payload, what kind of engineering goes behind that, right? Now, you said that one of the machines had 11 payloads, sometimes we went to 14 payloads. What design goes behind that, right?
Okay, so the mass of the payload is fixed. So for any system designer, the engineering designer, it is given that this is the budget what we have. Then when they design, the miniaturization is the one thing which always all space scientists will thrive for, because any weight which you want to put, that 1 kg is to amounts to certain amount of fuel, certain amount of budget. So anything they design, that miniaturization is a very important thing which they take into consideration in the design, and also the power requirement and the way it is going to be accommodated within the any space mission. So that is also miniature certificate. It is easily accommodatable as well. Like our Chandrayaan 3, the hazard avoidance, the camera, if you see, it is only 250 grams. That entire camera, it is only 250 gram only. So anybody designs and comes out, I have a camera which can do in 100 grams. These things will be picked up. We always, how best you are able to miniaturize, and you are also able to achieve the same accuracy what is required. Accuracy never will be compromised, but the how much mass you are carrying, that has to be always reduced, and in a way it is very compact.
Right. So the final payload is kind of fixed and everything is reverse engineered.
Yes, yes.
Designed based on what it can actually accommodate or cap.
Right. Yes, yes.
Right. Right. One of the things I always love asking engineers or scientists is, have you had experiments that have gone wrong? Right. So we always, we read about people's gasket design or bolt design, failing. From your career, have you had any experiments that didn't go the way you expected?
Our Chandrayaan 2 itself is the best example for us. Many of the things.
What I meant is in your area, remote sensing, personally, right?
Okay.
Have you had any experiments that?
Yes. So the in my area, even in Chandrayaan 2, there is a place where we have to find certain things. Many of the sensors we have developed. because almost 10 years before, mostly I was in the remote sensing, even for the other planetary missions we do and process. But currently, mostly I'm into this landing missions and this kind of development. So here, when we do, uh, as earlier I said, when we do this field test of our sensor, what we thought it never gone the same way as we expected in the first attempt. We had a series of failure only. Anything we do when we test it. So when the Chandrayaan 3, when we were developed this hazard detection system, one thing is when you do something first time, which has never been proved by anybody, and when you are doing it for the first time, and also when it is failing, so there is a lot of amount of pressure and the problem will be there that okay, how it is going to make it successful. I mean, so in we have seen that in maximum of the filters we had a lot of issues when we were realizing. Then finally we are able to make it into an successful system.
You know, one final question before we conclude. You know, we've always read about the leadership styles of you know, the ISRO present and former leaders, right? You know, in a book called the ISRO Personal History, Arava Mudan, who was in ISRO, the author of that book, he writes about how Sarabhai's leadership style was very different from, let's say, UR Rao, and which was very different again from Satish Dhawan. Right? In your 20-year-old career in ISRO, have you had an opportunity to work with some of the top leaders at ISRO, and can you share some experiences from that?
Here, mostly when I joined from my schooling, almost I think in the 9th standard, first I heard about this INSAT series of satellite when one of my teacher explained. That time he explained me about ISRO and that time about Kalam, and during that time I came to know much about ISRO anyway. So when I joined this Chandrayaan 1, during that time Kalam sir, he was the president of India, and after this launch, everything got successful. So he visited ISRO. So that time I had a very great excitement because that is one of the software which I developed. So he came to witness. So I could not be physically present, but when he witnessed, when I was very happy during that time. That is the one motivation point from Kalam to join for me to ISRO. And when I'm at the SAT ISRO working here, many of the seniors who were there here, the ISRO is always a very fascinating place for anybody to work. So that all the bosses is there. Here there is no the senior management or unit management. That kind of barrier will not be there. Whether it is ISRO chairman or anyone, we always have the equal level of interacting. So in my area, there are many people. They will not be popularly known to an outside, but they are all right from the remote sensing when it got introduced to even to date, who really realized the first time the remote sensing concept, the remote sensing processing, many the things anyway. So all of my earlier bosses were all very great to work with. Even the Karthikeyan sir, who actually called for this particular field, he is the image processing expert in our area. Even today, he is one of the pioneer person in our area who created many of the technology development during these 10 years. And the way they have carried and encouraged the people to continue even today. So it is always, everyone is so good to work with.
Thank you. Thank you, Mr. Suresh. And it was definitely a very fascinating lecture and a great learning experience for all of us. I will now turn it over to Ramanan for the concluding words.
Thanks, Mr. Suresh, and thank you very much for this fantastic talk. And I think it happened at a very short notice, but it has been a fantastic overview of the history from Chandrayaan 1 to Chandrayaan 3, and you set up the context very well. And you also brought in the personal flavor, which always makes these kind of lectures very interesting. And when you said that ISRO is a very fascinating place to work, I can see that pride on your face, and I hope people who see this lecture will, the youngsters, the younger ones who are in college right now or just out of college, this will it will inspire them to know more about ISRO's work, and maybe apply it to work for ISRO. Because I hope at least in my lifetime, I tell my sons that at least in my lifetime, I will see mankind settling on another planet, and I hope that that happens. So so fantastic talk. Thanks a lot, and thanks a lot, Varavamira Science Forum, to arrange this on a very short notice. This is a personal thing from me, and next month's lecture we'll let you know what the topic is going to be. So thanks a lot. Gopi, you can stop the live stream.
Stop the live stream. You can stay on Zoom.
Thank you very much.
Thank you, sir.